Yeah. And let's wait a minute or two until everybody is here, and then we can start. Okay, I'll stop sharing my screen. Okay, I think we can slowly start. So good afternoon, everyone. Welcome to this edition of the NITheP Colloquium. My name is Francesco Petruccione, and I have the pleasure of introducing today's speaker. And today's speaker is Dr. Ashleigh Hutchinson from WITS. She's a senior lecturer I need to, I already forgot. It's the School of Computer Science and Applied Mathematics. You know, this from university to university, school names change. Yeah. in the Faculty of Science at WITS. And also importantly, she's also the Assistant Director of the National Center of Excellence in Mathematical and Statistical Sciences. So she's a very important person. Yeah. And I'm very happy that she accepted this invitation, because typically, maybe I might say, without hopefully offending anyone, fluid dynamics is a little bit of a neglected discipline, at least in the theoretical physics community at the moment. Yeah? And I'm very sad about that, because in a quite distant past, I also worked on turbulence for a while. Yeah? And so I'm very keen to learn what has been going on in that area recently. And I'm very happy that Ashleigh accepted the invitation to be our speaker this afternoon. So Ashleigh, I will ask you in a minute to start sharing, or in a few seconds to start sharing your screen. But before then, I just remembered I have to tell everybody to please use the Q&A facility at the bottom of your Zoom screen to ask questions. And Dr. Ilya Sinaisky, who you also see at the top of your Zoom window, will manage the question and answer session during the talk, so that Ashleigh doesn't have to focus on questions while and chats while she's talking. Yeah. So Ashleigh, if you would like to slowly start sharing your screen, we are very much looking forward to your presentation.
Thank you so much, Professor. May I start?
Yes, please. The floor is yours. Yeah.
Well, thank you firstly to the organizers for allowing me this opportunity. It definitely wasn't the case where, you know, this is beneficial for me as well, and I hope that this talk is enjoyable. The title is Navigating Turbulent Waters, and I just want to give a shout out to some of my collaborators. We've got Nick Hale from Stellenbosch University, Kendall Bourne from WITS, who is a former master student of mine, and Professor Mason, who was one of my former PhD supervisors. So we've got a really good cohort of people working on this, and I would like to share some of the progress that we have made quite recently, in fact. Okay, sorry. Okay, so here's just a rough outline of my talk. I'm going to provide a very gentle introduction to turbulence, and then I'll start looking at some of the approaches that are used to model turbulence. There are many different approaches, so I'm going to focus on one of the relatively simpler ones, which is called the Eddy viscosity closure model. I will explain how all of this comes about, so if you're not familiar with these terms, that's not an issue at all. You don't have to pretend that your internet is just giving you issues now so you can leave the talk. I promise that I will go through all of that. Then for simplicity, I'll look at a specific example which involves turbulent wakes. I'll explain why I do that. Then I'll just provide some conclusions, and for those that are interested in looking at further work, just some references as well. Before we even hope to model turbulence, the first question we need to answer is, what is turbulence? This is actually not a very easy question to answer. Now, of course, many of us, we know what turbulence looks like, and we know when we experience turbulence. But the real issue is, can we come up with a good definition of turbulence? And that actually appears to be a bit of a struggle. So what we can do is we can list a whole lot of characteristics of turbulent flows in order to try build a definition around it. So here's just a picture of a turbulent flow. You can see that there are many different scales of motion. We've got large and small scales, which is definitely one of the characteristics of turbulence. Now, with turbulent flows, you'll notice that there are fluctuations which definitely appear to be random. So there is definitely an element of randomness to these turbulent flows, and it would be absolutely impossible to predict the motion of every droplet in a turbulent flow. You'll see that time and space dependency is also a central theme. As you move from different positions in a turbulent flow, you will notice that the behavior differs, and also with time. The motion is seemingly irregular, so there doesn't appear to be a definitive pattern that we can actually suss out. As mentioned earlier, there's a multitude of scales. One of the nicest ways to visualize this is to look at the eddies in a fluid flow, and you'll notice that you have different sizes of these eddies. Now, what's also very important about turbulent flows, and this is an idea that I'm going to be using later when I derive one of our models, is that it's impossible to repeat an experiment and expect to get exactly the same results. So if you have an identical setup, every single time you run that experiment, you're going to have different results and different velocity measurements because of the random nature of turbulence. And this fact can actually be exploited later, which I will show, in order to derive some of the mathematical models. With turbulent flows, there's also a sensitivity to initial conditions. So often a small perturbation in the initial conditions can lead to rather significant changes later on. And this is because turbulent flows and flows in general are highly nonlinear. Now, turbulence is considered one of the oldest unsolved problems in physics. Scientists may disagree on the statement, but I must say I'm definitely on the side of believing it is still unsolved. And hopefully I can convince you in this slide. Now, with turbulence, there is really no clear physical understanding of turbulence. We know what the characteristics of turbulent flows are, but it's difficult even to come up with some kind of robust definition of turbulent flows. What's also very interesting about turbulent flows is that many of the characteristics have actually been discovered through experiments as opposed to theory. Now, if there was a good theory for turbulence available, then surely it would make sense that we would be able to predict these characteristics from the theoretical model as opposed to seeing it from experiments. So this is one of the biggest reasons why turbulence is still considered unsolved. Interestingly enough, scientists are certain about the equations that need to be solved, which I'll go through shortly. So the equations are to some extent known. It's simple conservation properties of momentum and mass. But the problem is how to solve these equations. So that's one where the real issue comes about, is how to actually go about solving them. So we'll talk a bit about that. Also with turbulent flows, only in very specific cases can you even hope to understand or predict the transition from when a laminar flow becomes turbulent. So this is another reason why this is a very difficult unsolved problem, and we only have insights in very limited cases. Now, of course, people may argue, but if you know what the equations are, why can't you just use computational approaches to solve them? And the bottom line is the computational approaches that need to be used that directly look at solving the equations are very expensive. But also, computational approaches are not a substitute for actual understanding of a model. So we will be trying to look at theoretical models in hope that these actually will match well with experimental data. I hope to surprise the audience later on. Okay, so just to try prove, well, at least convince people that turbulence is still indeed unsolved, these quotes might have been changed over the years or taken slightly out of context, but here we've got Heisenberg, who says that when he meets God, he's going to ask 2 questions, why relativity and why turbulence. I really believe he will have an answer for the first. So that's pretty interesting and perhaps either quite discouraging or encouraging, depending on those who like a challenge. Here we have Feynman. Turbulence is the most important unsolved problem of classical physics. The question is, why is it so important? Well, not only is it interesting, I mean, for physicists, the whole passion about what you do is about trying to understand what is happening in the real world. But it's also important in terms of its applications in industry. So it has both societal interest and, of course, theoretical and pure scientific interest as well. I'll just touch on some of the famous scientists that have contributed significantly to turbulence. These names are taken from a book called A Voyage Through Turbulence, which my supervisor, Professor Mason, gave to me when I first started studying turbulent flows. So here are just a couple of the names. Some of these might be familiar. Reynolds, for those that know anything about the Reynolds number, will recognize that. We have Ludwig Prandtl. Prandtl, I'm going to be referring to his work quite a bit in this presentation. G.I. Taylor might be you're familiar. George Batchelor, considered the father of fluid mechanics. Philip Sapman, who believes that everything interesting in turbulence is just scaling. And we've got Kolmogorov at the end, who was a statistician primarily. So we've got a lot of different scientists from very diverse fields of research that gave turbulence a go. Before we even get to how complicated turbulence is, I just wanted to first of all explain where the governing equations for all fluid flows come from. The governing equations are actually quite lengthy if you look at the derivation, a couple of pages long. So I will just give the general ideas. Basically, you just consider a control volume. Sorry, I'm just trying to find my cursor. There it is. You consider a control volume in a fluid flow, which is fixed. Let's just suppose capital V is the volume. U here is the fluid velocity. It has 3 components. So for instance, if you're looking at Cartesian coordinates, you would have a ux, a uy, and a uz, or u1, u2, u3, depending on how you want to label it. So what you do is to derive the governing equations, you consider the fluid flow through a controlled volume, and basically you look at the conservation of momentum, which you will probably be more familiar seeing it as mass times velocity. In fluid mechanics, we work with density. It's easier to work with density. So in this case, we have the density rho times the velocity u, and then we scale the units accordingly to that. So the first equation here, it has 3 components corresponding to the 3 dimensions. So we get this equation over here, and this is just conservation of momentum. So just to recap, ui is the ith component of the velocity, rho is the density, p is the fluid pressure, and this mu here is called the dynamic viscosity. It's basically just a measure of the stickiness of a fluid. So if you think of syrup and compare it to water, it's harder to, let's just say, stir a bowl of syrup, and because it's got a higher viscosity. So this gives us 3 equations, and then we have another equation which comes from conservation of mass. Mass cannot be created or destroyed, and in the case where you don't have any sink or source terms, you just get the divergence of the velocity as 0. So we have 4 equations for 4 unknowns. The unknowns are the 3 ui and also the fluid pressure p. The fluid pressure p is very interesting, but unfortunately I probably won't have time to go into that now. Okay, so we start from the Navier-Stokes. That's basically always the starting point. And from then onwards, there are different approaches to modeling turbulence. So the ones that we won't be looking at today are simulations, which basically look at more direct approaches. So if you have direct numerical simulations, you look at applying numerical techniques to the Navier-Stokes equations. There's also large Eddy simulations that attempt to actually try and model the eddies in a turbulent flow. Then you have turbulence models, which I'm going to be looking at the most basic turbulence models in this talk, which are actually quite complicated, as you'll see later on. But in turbulence models, the goal here is, I would say, less ambitious than simulations. because what we do is we only solve for the mean flow variables. So we're not interested in the detailed turbulence structure. What we're interested in is just the mean flow, how that behaves. So clearly this is a limited description in that it only considers time average quantities. The mean flow variables are all time average quantities. And another issue that comes about, which I'll show you how it comes now, is that we need a closure model to complete the system of equations. So we need to impose some additional information so that we can actually solve the system of equations. And these closure models are derived from physical principles. So we'll look at the simplest type of turbulence models, which are called Eddy viscosity closure models. And the idea here is fairly simple, but quite brilliant. You take your flow and you divide your flow into a mean motion plus an eddying motion. The eddying motion basically just is a representative of the turbulent fluctuations. So for instance, with the velocity components, your UI bar is the mean velocity. The definition is shown over here. So it's just the integral over time with a 1 over t in front. So this is just the average. And then you have this UI prime, which is the turbulent fluctuation. For the types of models that we look at, we assume that if we had to average these turbulent fluctuations over a very long time period, then it would sum to 0. So that's quite important. So the goal of this is really to solve for the mean flow variables. We want to solve for the U bar I, UI bar. So what happens now is you take these mean flow variables and you substitute them into your Navier-Stokes equations, and then you average the entire equation. And what happens is that although the time averages of the fluctuations are 0, time averages of the products are non-zero. So what happens is that you get all these terms. If you look here, this is in terms of the mean velocity, mean pressure, but you get this additional term coming up, which is now in terms of the eddying motion variables. And these terms are unknown. So what happens in this case is that we now have more unknowns than what we have equations. So we need to figure out some kind of way to describe these terms so that we can actually solve for the mean flow variables. And that's exactly what the Eddy viscosity model does. So just to look at the equation on, well, just more about the equation on the previous slide, it was written or expressed in a bit more of a different form. To those that are familiar with the Navier-Stokes would have realized that. But there is a reason why it's written like that, and that's so we can identify the stresses with ease. So with turbulent flows, it's all to do with conservation of momentum. It's basically force is equal to mass times acceleration. That is really it, but perhaps just a complicated version of it. So the stresses that arise, we're dealing with stresses as opposed to forces because instead of using the mass, we use the density. So we've got isotropic stresses that act equally in all directions, and that comes about from the pressure. We've got viscous stresses, which can be both normal and tangential. It's because non-real fluids have viscosity. So as the layers, as the fluid flows, the layers interact with each other or interact with solid objects. Then we've got these turbulent stresses, which, as I've mentioned, are unknown terms. So we need to figure out some way to actually describe these. So the Eddy viscosity model approach is very simple, but sometimes the simplest ideas are actually perhaps the most brilliant. So what it does is it models these turbulent stresses in the same way as the viscous stresses appear. So instead of a constant dynamic viscosity mu, a turbulent viscosity mu t is introduced, and it's just assumed that these stresses can be written in the same form as the viscous stresses, with mu replaced by mu t. In the flows that we consider, mu is constant. However, mu t does not need to be constant, can depend on space, even velocity gradients, and a whole lot of other factors. So we'll be looking at different models that give an expression for mu t, and we'll evaluate these models to see how well they actually compare to real-world data. Just to point out with the Eddy viscosity models, the Eddy viscosity well, this should be effective, apologies. The effective viscosity is basically defined as the sum of the kinematic viscosity and the turbulent viscosity. Instead of working with dynamic viscosity, you can just divide by rho, so you can work with the kinematic viscosity instead. So what's nice about these models is that they provide a very simple description of turbulence, and the description simply is this. It says that when a flow is turbulent, it can be modeled as an increase in the apparent viscosity of the fluid. That's really quite simple and rather brilliant. So it's harder to deform a turbulent flow as opposed to a laminar flow. So it's almost as if the viscosity or the apparent viscosity is now higher. These models are also relatively easy to implement, not always very easy to solve. Again, it really holds true that we know what the equations are, but not always quite how to solve them. What's really quite amazing is that these models often agree well with experimental results. And I will be showing you successive approximations, and I will show you how they become better and better as you tweak your model. In some cases, exact solutions can be found. Now, of course, we have modeling error when we neglect certain terms, if we're looking at various approximations to the Navier-Stokes. But in this case, if we have an exact solution that eliminates all kinds of numerical error, so these are definitely advantageous from that point of view. Okay, so I realize this is a lot of information, and just so you know, my goal is really to provide an overview and not to go into the actual details. I will leave those the details to those who are interested, but hopefully you'll get a gist of the work that is happening in this field currently, and NIThePs. And sorry, Nick Hale, Stellenbosch as well. Okay, so we'll look at a specific example, turbulent wakes. So here's a really stunning picture of a wind farm. And you can see behind these wind turbines, we have these wakes developing. And if you look closely at this part over here, you can see the faint outline of another turbine just behind this one. And the problem is that this turbine is situated in the wake of the one in front of it, which actually leads to decreased power production. So studying turbulent wakes is not just fascinating, it also has industrial applications, which is something we like to play on, even though we often only just interested in the physics. All right, so just to provide some kind of overview of how we get the governing equations for turbulent wakes, it means that the Navier-Stokes equations are significantly reduced and a lot easier to deal with when we're looking at turbulent wakes. So it provides a really good starting example of working through all the models, all the closure models available. With the turbulent wakes, we implement what's called the boundary layer approximation. Really, in general terms, it assumes that the horizontal length scale is much greater than the vertical length scale, so we can make a whole lot of different approximations. So here we have a diagram of a wake. So here is an obstructing object, and here is the mainstream flow. So we've got this object, and upstream of the object, we've just got this laminar flow with components, x components of velocity capital U. We'll assume that this is constant. That's the simplest case to start off with. So as this fluid flows past this object, it's perturbed by this object, and we get a wake forming. We'll look at the far wake, which means that we are looking sufficiently far downstream. So that means that we define something called a velocity deficit. The velocity deficit is just defined as in this equation here. The stars are included to just show that we always work with dimensionless variables. However, being lazy applied mathematicians, we don't want to type those stars out, so they are neglected unless I just want to emphasize that it is non-dimensionless. So we use the capital velocity U here to find dimensionless quantities. So this means that the mainstream flow is 1 in terms of the dimensionless variables. So our velocity deficit comes from the x component of the velocity, and it's just 1 minus the velocity deficit is equal to the x component. So without going into the necessary details, the governing equations are actually shown here. V bar is the y components of the velocity. We're only dealing with mean velocity components, where the Eddy viscosity closure model has been implemented. So we get these two governing equations, which might look deceptively simple, but remember here, E can depend on a whole lot of things. Doesn't have to be a constant. We have some boundary conditions, which you can see from the diagram. As we move off in the vertical direction, the velocity deficit tends to 0, as we expect, as we further away from the disturbance. It also does so quite slowly. We can expect that the first derivative is 0 as well. On the axis of the wake, you can see that the velocity deficit is a maximum. And because we will only look at symmetric wakes, the y component of the velocity disappears in the axis as well. These types of problems are very interesting. The governing equations are homogeneous, and so are the boundary conditions. So what we need is an additional conserved quantity to help solve these equations. And this is actually just comes from the momentum equation here, and you just integrate this across the wake. This YBX is defined as the boundary of the wake. In this diagram here, you could expect YBX to actually be infinity, as W bar will never reach 0 at a finite value, but that's actually not true for all models. So we've just left it as YBX to denote the boundary of the wake. So just to discuss some of the experimental data that we will be looking at. So this is based on data that was collected using wind tunnel experiments. It was published quite a few years ago, but this is an excellent data set, which is why we used it here. So this will be our reference, and we will compare our models to this data as we go along. With the experimental data, the scientists here, they looked at many different kinds of wake generators. So for instance, you can have an airfoil, a cylinder, some flat plates. So what happens is, in order to enable all of these to be compared, they rescale the variables so that they can get a best fit curve which satisfies these two properties here. I'm just mentioning this because we are going to be comparing our results to the best fit curve. Unfortunately, the actual data points were lost decades ago. They were saved on tapes, so we don't have access to that. But we'll use the best fit curve, which, as you can see, collapses rather nicely to fit the data. We should just be wary a bit about the edges because the data is clearly a lot more noisy there. So when we compare our models to the data, we need to rescale our variables so that we can compare it. Okay, so I guess the starting point is always to look at the simplest model. The constant eddy viscosity model is not something new. It's something that's been well known. But basically, it just assumes that our E here is a constant. Why not just look at the simplest model? So you can solve these equations by using similarity variables or just seeking for scaling solutions. Perhaps this is a method that comes up a lot in fluid mechanics and actually many branches of physics. There are numerous ways to derive these, but I've just stated them here. And you can substitute these variables into these equations, and eventually you rescale everything so you can compare to the data, and you get this normalized profile. So again, this is not, from our side, this is not new. We just wanted a good starting point to compare the later models. Okay, so when comparing this to the data, this is what happens. You can see here that the data is given by the solid line. The dots are the constant eddy viscosity model. Now, this is a very simple model which has an exact solution, which is great, no numerical error. But we see that, surprisingly, this fit is actually not too bad, except where you get near to the edges of the wake, where you can see that you can see the deviation that develops quite quickly. What was important about re-looking at this model that has been looked at so many times is that we want to understand why this model caused issues at the boundary. And we realized that it causes issues because of one simple fact. The eddy viscosity in this case is finite at the boundaries. So because it's constant, no matter where we are along the vertical axis, it's always going to be the same value. What we actually want in the eddy viscosity models that we look at is for this eddy viscosity to disappear. Now, the eddy viscosity is associated with the turbulent motion, and we would expect that our turbulent wake would merge smoothly with the mainstream flow, which is laminar. So it actually really does make sense for the eddy viscosity to vanish at the boundaries, because that's where the transition to the laminar flow, which should have a zero eddy viscosity, is happening. So that's what we want. So it was good re-looking at that. Okay, so I want to move on to Prandtl's mixing length model. Prandtl looked at this. He wanted to improve on the constant eddy viscosity model. I also thought that the audience here might appreciate some of the work, the derivation of this model, because it actually involves physical principles such as the mean free path in the kinetic theory of gases. So this is just an approximation because, of course, we are now looking at a macroscopic scale, larger scales perhaps is the better way of saying it. So it really is an approximation. But let's just look at the simplest case, which corresponds to parallel flow. So basically, we've got a mean velocity component in the x direction, which only depends on y, and we've got the turbulent fluctuations, u prime and v prime as well. So with turbulent flows, what happens is that the particles come together into fluid, forming fluid lumps. They stick together, travel some distance before they disintegrate and mix with the surrounding flow. Before they mix with the surrounding flow again, they maintain their properties such as momentum. So really what this model does is it looks at a fluid lump that's situated, you can see on this dotted line here. And in this model, it supposes that it's the turbulent fluctuations that are responsible for displacing this fluid lump to some higher position where L prime is the displacement. So during this transition, this fluid lump will retain its properties, but after this point, it will mix in with the surrounding fluid. This whole L prime is related to the concept of a mixing length. So it's basically the distance traveled by a fluid lump before mixing in with the surrounding fluid. Because turbulence has a random component, these L prime fluctuations are indeed random. So what we really want to look at is the variance of these in our model later on. So in order to measure the strength of the fluctuation, we know that this fluid lump retains its momentum during the transition, which means that it must retain its velocity because the density is constant. So as a measure of the strength of the fluctuations, we look at the difference of the mean flow in the new layer, and we subtract the mean flow velocity of the fluid lump. So that just gives you an indication of the strength of the turbulence. So the stronger the turbulence, the greater this lump will be displaced. We then just look at a Taylor series, and we're going to neglect terms of order L prime squared, and then really just hope that those are indeed small, and the approximation we made is not a problem later on. So that's just a bit of hope over there, but nevertheless, it remains to see what happens. We can use conservation of mass to show that u prime and v prime have opposite signs. So when a fluid lump is displaced in the y direction, this means that the velocity fluctuation in the y direction must be positive. There must be a velocity component in the y direction in order to displace a fluid lump in that direction. So with our fluctuations, we can finally gain some insight here. So we write our x components of the velocity as u bar y plus u prime. And basically u prime here is just set equal to minus delta u here. So this is our expression for our x components of velocity, and we've also got the y components here. So we just assume that this constant is of order 1, and it just basically states that u prime and v prime have different signs, but they also might not have the same magnitude. They could differ in magnitude, which is why this is included here. And it's thanks to my former master student, Kendall, for this nice diagram. So with Prandtl's mixing length model, based on this physical approach, you can actually write the turbulent stresses in this form over here. So you just take the expressions for u prime and v prime, multiply them together, and this is what you get. With the eddy viscosity closure models, the whole goal is to determine these stresses in terms of mu t. And if we compare these two expressions, we can actually derive the expression for the turbulent viscosity. This L squared is just C times the variance of the standard variance of L prime. For wake flows, because we made the boundary layer approximation, which assumes that the horizontal length is much greater than the vertical, we can actually just simply replace this derivative here by the partial with respect to the velocity deficits. And that's because of the boundary layer approximation. So essentially what we get is we get an effective viscosity, which has been scaled, not too important the scaling, but what I just want to mention is it's the sum of the kinematic viscosity and this newly derived turbulent viscosity that was obtained from physical principles. So what Prandtl did many decades ago, 1930s, I think, I hope that's correct. So what he did is he looked at this effective viscosity, but he neglected the kinematic viscosity term. The reason why he did this is because he said that the turbulent viscosity is so much greater than the kinematic viscosity, so why not just neglect it? During some work done in my PhD, I looked at what happens when you include it, and the results were very insightful, so I will just share a bit of that now. So some more, jumped a little bit there, some more of the issues. Prandtl again assumed that the kinematic viscosity can be neglected, but this is actually not true on the axis of the wake and at the boundaries, because that first derivative disappears at those points. So that's certainly not true for all regions of the wake. So we can look at an extension for that. Another issue is that the mixing length is unknown, so we don't know what this L squared is. We just assume now for now it just depends on X, but we actually don't know what it is, and Prandtl had to impose an additional hypothesis. Another issue is that a finite wake boundary is predicted. This might not seem like such an issue, but it really does become an issue when you're looking at the transition from the turbulent flow to the laminar flow, which you would like to be nice and smooth, which does not happen if you have a finite wake boundary. It was perhaps very interesting that Prandtl neglected the kinematic viscosity because he developed boundary layer theory, which assumed even though the kinematic viscosity is small, it does have importance in certain regions of the flow. So there are a couple of solutions to these issues. Prandtl knew the issues up front, so he looks at an extended model, which will be largely later on the focus of this talk, but the same issues still remain. The boundaries, we still have that the turbulent viscosity vanishes at the boundaries, and the mixing lengths, there'll be two in this case, and I'll share that derivation just now. Those also remain unknown. So we still have many of the issues present in the original model, although it definitely is a better approximation to the data, as we'll show. A lot of these can actually be resolved by including the kinematic viscosity, which is the work that I did in my PhD. And it was very insightful looking at including the kinematic viscosity because it actually resolved most of these issues. Okay, so including the kinematic viscosity, yes, it resolved those issues. It allowed the mixing length to be determined without imposing any additional hypotheses. It was good. But when it comes to the actual fitting to the data and comparing it, it doesn't actually appear to have much of a role. So although it's important in the mathematics and the modeling, it doesn't actually appear to be too important in the actual fit to the data. So here is a plot of just the Prandtl's original model, which excludes the kinematic viscosity and the data. So all these graphs were done by Nick Hale, who was also responsible for the extended Prandtl model and the hectic numerics that I will show later on. So just some observations. Again, I've mentioned this, but if you look at the fits of the data, it's a little bit underwhelming, to be honest. It almost looked like the constant eddy viscosity model was a better fit. I mean, you can kind of see that maybe it better approximates the data towards the edges, but certainly on the center line, it doesn't appear to be too good. So that was a bit disappointing. But nevertheless, we decided to look at Prandtl's extended mixing length model. This model has not been well researched because of the additional complexities that actually results when you implement it, which is why we needed a numerics expert to actually help us with this. It was beyond what we were able to do with the knowledge that we had, none of us being experts on numerics. So Also, another issue with the Prandtl extended mixing length model is in the literature, there doesn't appear to be a very good derivation of it. In fact, it's just stated without proof. So one of the things that we wanted to do was to really understand how this model is derived. And we did manage to come up with some really cool ideas, which I'm going to share just now. But just to give you an idea, the whole point of Prandtl's extended mixing length model is to improve on the approximation obtained from the Prandtl model. And it looks basically at this term here within the absolute values, and it approximates that better. So here is where the creative ideas were really flowing, and it comes from the idea of using an ensemble, which is quite common in physics modeling. So in this case, we just need an ensemble with two members. So we just have two experiments. Now remember, when you try repeat a turbulence flow experiment, you'll get different measurements each time. So we suppose that we have two such experiments, and for the x components of velocity in the one, which is denoted by U1, I've got an L1 prime associated with it. And in the next experiment, I've got an L2 prime. So these will correspond to the different measurements. So what's important to note is when you take the derivative with respect to y and the average, you'll notice that the average of all these derivatives is equal to this over here. So we can rewrite this term as this expression here. And this step, which just basically says that the product of the averages is the average of the products, is true for variables that are independent. We definitely are working with independent variables as we are considering two different experiments. So there's no issues there. So what we do is we just take this expression, we plug in the values that we have, and basically we get this coming out. So the additional term that has now come out is this term with the second derivative. In the previous model, we just would have had this term here. So the eddy viscosity looks slightly different. We've got a second derivative term, but we've also got a second mixing length coming out. So that's important. We've got two mixing lengths. And again, we can extend this to wake flows because we're using the boundary layer approximation. So we can write our effective viscosity again as the sum of the kinematic viscosity and our modified turbulence viscosity. It's easier to try work with rescaling these variables so that we can make things look a bit nicer. And just redefining some constants, we can introduce a beta and alpha. So what we really want to solve is this equation here. This equation is difficult. I'll just point out why it's so difficult. We have squares, we've got this all under a square root, we're going to have branches of solutions and all sorts of weird stuff happening. One of the goals that we wanted to achieve in this work is, like with my PhD work, when the kinematic viscosity was included, we wanted to find out what would happen if we included the kinematic viscosity in this model as well, which was neglected previously. So when we include the kinematic viscosity, basically what happens is, well, okay, here's just a bit on how you want to solve. We just use similarity variables again. But basically, when you include the kinematic viscosity, the same advantages come up in that the two mixing lengths can be determined instead of imposing any additional hypotheses. So the system and the model is quite close in the sense that you can derive everything from the model. So here is the reduced equation. So these similarity variables or scaling solutions are very nice because we can reduce our PDE to an ODE. Again, still very difficult to solve. Oh, wait, I ruined the surprise. Okay, so just a bit about the numerics. I'm not going to go into it too much. This was definitely Nick Hale's domain. Us not being numerics experts, we had to get one. And this was not easy, solving this problem. What was really cool is that it took a lot of both insights, physical insights, and obviously a great knowledge of numerics to try to put this all together. Numerics is not just about applying some scheme to a differential equation. You need to understand the differential equation so that you know what scheme to apply. And in order to achieve that, you have to have a good understanding of the physics. And that's really where the link between numerics and physics is so important, and it cannot be ignored. So anyway, of course, we hoped that this model would be a better fit because it hadn't been really discussed in the literature. So when we did look at this, lo and behold, we got this amazing, absolutely amazing result where you can see that the model almost lies, along the curve. It really is quite incredible. So I think that was quite an achievement, and it was nice to look at models that were developed many decades ago, but also to improve on them, which often people progress with the latest trends, and which would include numerical simulations. But in this case, we were able to get some insights into older models and revamp them a bit. Okay, so yeah, like I said, the fit is incredible. Definitely, worthy of a celebration at the PIG, but we were very happy with this. Okay, so you might ask what's next, because that's such a brilliant fit. Well, a couple of things are next. We know that the data was quite noisy towards the edges. We definitely do not have the equipment to rerun experiments of that nature. Perhaps the engineering departments might be able to assist there. But to see if we can obtain more accurate measurements would be important, because the better the fit to the data, we need to make sure that the data, also the error is minimized in that. So experiments will definitely be in the future, but in terms of redesigning the model, when we looked at the ensemble idea, we only considered 2 experiments, but why not consider N of them? So the next thing to do would be to look at that, and I have no doubt that the numerics will be even more complicated. So just some conclusions. Looking at all these previous models was really useful, because a lot of insight was obtained, and it enabled us to go forward and gather the characteristics that we wanted of a closure model. Awesomely enough, we were able to derive the extended Prandtl model. To the best of our knowledge, we have not seen a derivation in the literature before, and it was rather incredible. The extended Prandtl model is very, very, very accurate. So in terms of applications for engineering purposes, it would be a good one to use. This is often coupled with machine learning approaches, but often you need a starting point even for these approaches. So this extended Prandtl model would be a nice starting point. Okay, so thank you very much. Here are just a couple of references, some of the work for my PhD, and this is just if anyone has, if you want to look at anything further. Thank you very much.
Yeah, thank you very much, Ashleigh, for a fantastic overview and leading to some very interesting new results. Well done. Thank you very much. I really enjoyed the talk. Ilya,
thank you for this opportunity.
No, thank you for sharing it with us. Ilya, are there some questions for Ashleigh?
So far, there is no questions, but I've got a couple of questions, if Ashleigh don't mind.
Okay, maybe we
and
use
and just keep in mind that yes, I have no good idea about hydrodynamics, so my questions might be a little bit naive. In your ensemble equation, you started with the 2 representatives, and why your equations which was produced was not symmetric with respect to the swapping of them?
So do you mean symmetric as in, sorry, let me just clarify for that. Symmetric as in, sorry, can you just further elaborate on that?
I mean, like, if I just look at your equation with the if I swap your experiment 1 and 2, I will get a different equation, in the sense like, is there any order between these experiments, or?
I think at this stage, so the only difference in those 2 values was the L1 prime and the L2 prime, which can be representative, well, it's just, those are random variables. So in terms of, you can look at them at maybe at which the order in which you did the experiments, but because turbulent flows are time dependent, we would definitely expect, even if we tried to repeat an experiment, we would expect different results. So it was really the mixing length, that random fluctuation, that displacement, that would differ in those 2 experiments if you had to measure it.
Mm-hmm.
I hope that answers, sorry.
Okay. And another question which I have, it's probably a little bit more more broad questions. Like in the derivations which you demonstrate, there is an assumption that that you can do an expansion, that you can do a Taylor expansions, and how this is justified, because my kind of naive understanding of turbulence that there is no analyticity and essentially nothing like this could be done.
So that is a good point, and I think when everyone looks at the derivation of that model, I think anyone would proceed with caution. Prandtl, when he derived his model, he made it very clear that this is a very basic approximation to turbulence. So there are definitely errors with that. Even the size of the L prime, stating that it's sufficiently small, I mean, that could even be an issue. You would have to compare that to the size of your lumps. There's not much actually, spoken about in terms of the size of these fluid lumps. So there definitely are a lot of issues. I think despite its issues, what's important is that the fit to the data is still quite good. So I think really that is the point to highlight. Like a lot of mathematicians would say, a lot of models are, not very good, but they all have their uses. And in this case, it was quite interesting to see from such a broad general description that it actually did match the data fairly well. But I agree with you, there are countless of criticisms in that. It's always just been surprising that it's been a decent fit to the data.
Okay, thank you. And Andre, you can ask your question.
Hi, Ashley. My name is Audrey Berger. I'm from Northwest University.
Hi, Prof.
My name is Audrey, not Prof.
Oh, sorry. Okay. Hi, Audrey.
We analyze magnetic field data from spacecraft because we are interested in how particles are scattered by this. Lots of turbulence, but very, very different from what you're doing. To give you some background, if I'm asking a stupid question or two stupid questions, when you do your derivation, you assume that the density is a constant. How good an approximation is that?
So for incompressible flows, that is a good question, because for fluids such as water, that's not a bad approximation at all. If you're looking at air, it's still not too bad, but of course there can be variations. Generally, what they try to do experimentally is to try and measure these variations and then show that they are quite small. From what I've seen from the experimental results, they haven't concluded that there's been a significant change in the density. So they have quite consistently neglected any changes.
Okay, my second question is, the data is clearly, it has to be from a 3D experiment, three-dimensional, but your solutions are all in 2D.
So, okay, thank you for that question. In these flows, turbulence is three-dimensional, but what essentially we are looking at is that two of the dimensions are more prominent than the other one. So you can suppress the dependence in the third dimension. That's generally what is done in the case for wakes. You could have, let's just say, an axisymmetric object where you have, like, let's just say, a cylinder, and then you would have the radial symmetry. But in that case, the theta direction is probably, that dependence is suppressed, and then you will just have the 2D plots.
Okay, thanks for that.
Thank you.
Okay, so and we've got a question in Q&A, and that's thank you for the very nice talk. Did you try to compare your model to other turbulence models such as K epsilon? Also, when calculating the time average of the velocity, what is the period t that you consider in the integral? See the first slide.
Yeah, okay, thank you for that question. So with regards to further models, the K epsilon model, that is definitely the goal. At the moment, we're still trying to, I'm actually working with an honors student, Bafana, I'm not sure if he's here. We're working on what it really means to compare a model to data. So we first want to get that clarified before we move on to more complicated models. But the whole goal of this project is actually to build up and compare the models as we go along. So we just started off as simple as possible, but K epsilon is definitely on the cards for future work. And so we want to eventually be able to compare all these models. With regards to the time average, you know how applied mathematicians work. They often make assumptions and then just hope they hold. That time t, that time interval t, is just in the definition considered to be something sufficiently large so that the averages are indeed independent of time. So you can't make that interval too short because there still might be some time dependence that's left. So just something long enough which I guess would vary between types of flows. You can get, let's just say, extremely turbulent flows are fully developed, or you can get more intermediate flows, turbulent flows. So it really would depend on the type and the flow, but for the theoretical purposes, for the modeling purposes, it's just assumed to be something large enough.
Okay, thank you. And to the best of what I can see, there is no more questions.
Can I ask a question, Ilya?
Of course.
Yeah. Ashleigh, when in a previous stage of my life, when I was working in Turbulence, there was lots of hope in lattice gas models and other stochastic approaches to turbulence. I've not really followed it. Is it still something that people are hopeful for, or is it not fashionable anymore?
You know, I mean, that's the point, I guess. You know, what is fashionable? I can honestly tell you that a lot of the research at the moment has definitely been dedicated to the more computational methods. So I will have to check up more about the lattice models. But of course, I do know that the current trend is to utilize technology. I wouldn't be surprised if maybe it has been neglected, just like some of the other more theoretical models.
Okay, thank you.
Okay, and we've got a question from Camille. So, I thought that turbulence was important for aeronautics and even car F1 industry. So I thought the turbulence was already quite well understood, but apparently not so much. So do you think your more accurate model could have some impact in these industries?
Definitely with aerodynamics. So if we're looking at flows past a foil, that could have some impact. We would have to really look at those cases in detail. Often the mathematical models that are used in turbulence are dependent on the situation that you're trying to model. It's another thing that makes them so difficult, and that makes turbulence so difficult. I would expect that there would be, especially with aerodynamics, absolutely. With cars, drag, if you know, understanding more about the drag, the turbulent drag and all of that, definitely could have an impact. It is surprising, I agree with you that turbulence isn't well understood. I guess that's what is interesting, is that often these techniques, the models do lead to pretty decent results, but that doesn't really mean that they're very well understood either. So I guess that's one of the real challenges of the turbulence modeling, and also because for each situation, you basically have to look at a different set of models that's applicable to that situation.
Okay, thank you.
Okay, if there are no more urgent questions, then Ashleigh, thank you very much again.
Thank you for having me.
For the excellent talk, and I'm sure everybody enjoyed it very much. And I hope that we'll have in future more talks on unsolved classical problems and not just unsolved quantum problems. Yeah, yeah. No, thank you very much, Ashleigh. It was really very nice, and I hope we will stay in touch. Yeah, in a social distancing sense. Yeah, of course. Yeah.
Of course. Thank you, everyone, for attending this talk. If you have any questions, please feel free to email me as well.
Yeah, thank you very much. And the announcement for next week's talk will come out very soon. Yeah. So
perfect.
Thank you very much, everyone. Have a good afternoon, and thank you, Ilya, for the moderation of the questions. Ashleigh, thank you very much. Have a good evening. Bye.
Thank you. Bye-bye.
Bye.